Hello, I'm Dr. Pandora Hope, a Principal Research Scientist at the Bureau of Meteorology. I lead a team called Weather in Context, and I'm also a lead author on the Intergovernmental Panel on Climate Change. Today I'll talk to you about the climate variability in your region and the wider Murray-Darling Basin. I'll present results that are mostly available freely, but I'll also talk about some of the new results that are emerging out of our work under the Victorian Water and Climate Initiative that I think Jeff will tell you about a bit later. From today, I hope you'll find the information useful for your planning and policy development purposes. And I hope you enjoy the day. So why might we be interested in climate variability and change in your region? For me, it's really understanding the physical drivers of what's causing that variability, and that might interest you too, but it might also for you be about understanding the risk that climate variability and change brings. Before we get into that, I'd like to give some thanks to the people that have been working with me on this, mostly under the Victorian Water and Climate Initiative that I think Jeff will talk to you about later. So how do you include climate information into your planning and decision making? Firstly, think about your system. How can you characterise the risks that you face, and how do you make decisions in your system? And those risks are integrated. It's not just climate on its own. It's linked in with all the other factors that build risk across your system of interest. So perhaps you could consider scenarios. What are some high impact, low probability events that would break your system? Or perhaps there's some low impact but frequent events that would stress your system. Or maybe some shocks, such as infrastructure breakdown. What if the locks and weirs in the Murray broke with major flooding? What would that mean for your system? There's also external factors that you would need to consider. The insurance and finance sector are very interested in the climate risk of their policy holders, and they might decide that they don't want to finance or insure you if they see your risk as too high. And then there's policy changes, both from the state and federal level. So think about those, and then what is the resilience of your system? How well can it withstand these shocks or changes? And if something does happen, how long will it take for you to recover, and how many times can you withstand that? And when do you need to make changes? So if we think about the climate and weather information that you have to hand, in this presentation I'll mostly be talking about the long-term climate record. With that, down here in the bottom left corner, you can characterise your current climate risk exposure. And that will inform your near future projected risk, because we assume that the recent climate is some indicator of what's to come over the coming decade. With that, you can go forward into your operations and look at the weather right now, what the weather forecast is, and that will inform your operational decisions. Looking more broadly, you might also consider what's happening further north and think about, say it's raining here, but it's very dry up north, and it has been for some time, and the seasonal forecast is for continued dry conditions there. That might impact your system and inform your tactical decisions. And then right through to future climate risk, which will inform strategic policy and decision making. So try and think about all these factors as we go through the presentations and workshop today, and what that means for your system, your policy, and the decisions that you're making. So here I will be talking mostly about observed variability and change, highlighting Mildura and the wider Murray Basin, briefly touch on baselines and the future cool season rainfall, and then changes in the weather and extremes that we're getting from this Victorian Water and Climate Initiative work. The recent drought, briefly touch on that, and changes in temperature and evaporative stress, and some of the ways we're looking at that, and finish up with a brief seasonal forecast. So firstly, there's a lot of information out there, These are documents that were actually the Natural Resource Management Plan for Climate Change for the Mallee region, published in 2016, and it describes the average daily maximum temperature of the region and the daily rain and the average annual rainfall. And you can see that I can see overall it's very dry and quite warm, particularly in the north. One thing I notice is that the magical 600 millimetres that you need over a year before you get substantial runoff is something that just isn't seen in these averages. So it's very dry. Also, more for my benefit perhaps than yours, the Mildura seasonal temperature variation on average is from warm to very warm through the seasons, and interestingly very cool in those winter night times. Rainfall, as I said, was very low and relatively consistent throughout the year, with about an average of 20 to 25 millimetres each month. If we then start to think about the changes, we can draw on documents such as the climate guides produced by the Bureau of Meteorology, CSIRO and Farmhand, and they describe things like some decreases in rainfall over the last 30 years and increasing temperatures. Interestingly, spring frosts have become more common and are occurring later, and you can follow those links to see what you can find in those brochures. If we look more broadly, the annual mean temperature trends from 1950 to now show that Australia is warming everywhere. So this is a really clear signal in the climate of how things are changing. I was really interested by this pattern here. Let's see if I can get the mouse to work. Where we can see a bit of a cooler warming, less warming in the Mallee MCMA region, and I wonder if that's linked to the evaporation due to irrigation in the region. We know in the northwest of the country there's been a very strong upward trend in rainfall there, and that's why we see less cooling there, so that could be the case. Now if we come back to the daily timescale, we can look at the days over 38 degrees in at Mildura Airport. And there's generally an upward trend, but there is some year-to-year variability, such as here in 2010 when we see this big drop. And we know that that's caused by the large-scale drivers, such as El Niño and La Niña from the Pacific Ocean. And in the case of 2010-11, it was particularly the La Niña phase of the Pacific variability that caused that very high rainfall totals there. And the Indian Ocean also plays a role, with the Indian Ocean dipole phase being very important for southeastern Australian rainfall. The southern annular mode can also influence the region, as it indicates a vacillation of the jet to our south, and when it's further north it can have different impacts from when it's further south. All of these contribute to the variability of the weather systems that come across the region, the fronts, the lows, and as I'll talk about later, the thunderstorm environments. Looking at the rainfall at Mildura Airport, you can see that 2010-11 spike in the annual rainfall associated with the La Niña conditions. This is the same as back in the mid-1970s, when there was a similar spike through a string of La Niña years. Breaking that down by season, in the red we have the warm season from November to April, and you can really see that that rainfall in 2010-11 mostly fell during the warm season. And think about that as a factor in how that influences your systems. The winter time rainfall, the cool season rainfall from May to October, has been relatively consistent through the period, but there have been some declines in recent years. If we look more broadly at the Murray-Darling Basin, we can see that same signature of reduced rainfall overall in recent years, but strong increase during those La Niña years in 2010-11 and in 2016 is evident as well. We really see quite high variability through the years, and this is something that I find really interesting, but it makes it a bit more challenging for planning perhaps. We know from climate change science that the trends across southern Australia are easier to attribute to increasing levels of greenhouse gases, and we can look at the trends in just Victoria's rainfall, and you can really see that millennium drought from about 1998 through, in theory it ended in 2009, but actually right through to the present day it really looks dry except for those 2 La Nina episodes. So what's going on? So I'd like you to focus on the black dots that you can see over here on the left, and this one here represents the millennium drought from 1997 to 2009. And we can see that relative to a baseline from early in the 1900s, so 1900 to 1959, there's been about a 15% drop in rainfall through that period. And this is just for Victoria. As I said, we're more confident about what's going on there in terms of the greenhouse gas signature. We compare that with other droughts, the World War II drought, which was from 1935 to 1945, and that was much less decline over the Victorian region, although perhaps more extensive through the Murray-Darling Basin. What's interesting though is that if we extend the period through to the full 22 years up till now, we can see that that drying has actually persisted. If we look at that greenhouse gas signature forward in time, we're looking at 20-year intervals over time, and we start to look at the blocks now here. And these are actually climate model simulations and the range that you get from different climate models in the projected future. So this one here is from now until 2039, and then on from there until we get to the end of the century, 2080 to 2099. And you can see that although the models diverge a little bit from each other, the signal is very much the same, that we do expect drying through Victoria in this cool season rainfall right through the coming century. So that makes us ask, which baseline is the best baseline to use? And we're mostly thinking about the current baseline, which is for predictive purposes. So pushing through into the decade or 2 or 3 that are coming, what's the best baseline to consider as our current climate? So DELP recommend now 1975 to date. So this is because the recent 22 years have been so dry that we really want to capture that shift to drier conditions compared to earlier in the record. Another option, if you're thinking about water resource availability, where you really don't want to make the error of not having enough water, is to consider a post-1997 step change scenario and push that forward in time. So why are things changing? As I said, we've been doing research under the Victorian Water and Climate Initiative, and we've looked at the weather systems individually, so identifying each front or low, and also identified thunderstorm environments. And we can look at that in the cool season, comparing a recent period from 1998 to 2015, which includes that millennium drought, compared with the earlier 17 years from 1979. And so we see that rainfall from fronts and lows has decreased, while rainfall from thunderstorms in this area has decreased, but around the coast has actually increased. And this is exactly what we expect from climate change. If you look at the warm season signature, that's really drawn out more. We expect that the warm thunderstorm type environments, that real convective rainfall with lots of uplift and smaller storms, will increase the rainfall, but the fronts coming through will reduce the amount of rainfall that they bring. And that's certainly a signature that we're seeing in this work. Another aspect we can think about is the hourly heavy rainfall. So this might be of interest for stressing urban environment or your particular horticultural interest. And if we look at rainfall events over 12 millimetres per hour, we can see that they are generally increasing over time. Another way, if we look at the tail of the distribution, the curves to the right are more recent, and that last one is 2005 to 2014, which is our most recent period, and it really is a big shift to the right. Interestingly, a lot of those extreme hours occurred on February the 4th in 2011, and we think it's associated with the moisture brought by some tropical lows in late January and Cyclone Yazi in early February. If we now think about how the individual weather systems relate to stream flow, we can look at individual catchments, such as the Campaspe catchment here that runs into the Murray, and think about So an interesting facet that we've found about the catchments in red is that during the Millennium Drought, the runoff that they generated from the rainfall was less than we might have expected, and that signature has continued since the Millennium Drought has ended. So we explored the weather types that contributed to that change and found that indeed the lows that we might expect would generate good stream flow because they're widespread and persistent, have reduced in their number and have contributed a little bit to that change in the rainfall runoff relationship. But there are other factors that are probably more important, and so that research is still ongoing. If we then think about the other factors that might influence your environment, such as the temperature or the evaporation, the temperature is a really clear signature. There's just a warming trend everywhere right across the Murray-Darling Basin. Combined with that, we also see a decrease in the relative humidity, so the air is getting drier over time. And that can combine to make increased evaporative stress. And this is a time series from 1975 of the upper and lower Murray Basin. And so you can see in the blue, in the north of the region, the last 3 years of drought, 2017, 18, 19, are quite evident with this metric. But interestingly, in the lower portion of the Murray Basin, it's really only the earlier part of that period, which surprised me. So what other information sources are there? At the Bureau of Meteorology, we're working towards a seamless service where we can look at the past climate, as I've shown you today, the short-term weather forecast through into the seasonal forecast, and then drawing on information produced by great research projects such as the VCP-19, we can then draw on those and build hydrological projections from those. And finally, I thought I'd show you the seasonal forecast for the coming season, July to September, which shows very high probability of above median rainfall right through the region. So I hope you enjoy the rest of the workshop and really get some good information that you can use in managing your systems and making your policy. Thanks.